Okay, hello everyone. Welcome to this third part of lecture on the fundamentals of spectrophotometry. So, in this video, I'll be discussing to you the limitations of Lamberts Law. Remember that in order to obey the Lamberts Law, the absorbance must be equal to epsilon B times C. Epsilon is the molar absorptivity, B is the path length, and C is the concentration. Okay, these are the conditions that must be followed. Light must be monochromatic, path length must be constant. Okay, as I said, that the length is in millimeter or centimeter, but in most cases it's one centimeter. And oftentimes we use square cubit, but some Spectronic 20 uses circular cubit, just like what I have used in our demonstration in the spectrophotometry. And samples should not fluoresce or phosphoresce. Fluoresce, okay, or fluorescence, here the emitted light has longer wavelength. Remember, the the purpose of the purpose of prism is to select the light that depends on the wavelength of interest, okay, and that is the light that would pass through the slit. So we don't select this, okay, we don't select an object that fluoresces. Also, a phosphorescent, okay, a material that phosphorescent materials does not immediately re-emit the radiation it absorbs. um, Remember, as I said, from ground state, okay, as the electron of the material of the sample absorbs the energy of the proton, the electron moves to the excited state, okay, and it goes back rapidly or very quickly to the ground state, and when it does, it emits energy. Phosphorescent material does not emit uh, or re-emit radiation rapidly. Okay? Other limitations of Beer-Lamberts law: um, avoid scattering of light. Okay? And as much as possible, the chemical composition is constant. It's the sample in the cuvette does not or the chemical composition in the cuvette does not change. Okay. Beer's law states that A, or absorbance, is proportional to the concentration of the absorbing species. The, the more concentrated, the higher the absorbance. The less concentrated, the less absorbance. Okay? Um, Beer's law applies well or works well for dilute solution. If you are going to prepare solution, preferably it's less than 0.01 molar. Okay, we don't prepare a very concentrated solution. Okay, it's been said that Beer's law works well for dilute solution, preferably 0.01 molar. What happens in concentrated solution? In concentrated solution, we know that there are many solutes, okay, and solute molecules influence one another as a result of their proximity. When solutes get close to one another, their properties, including the molar absorptivity, changes. Remember, um, molar absorptivity, that is the inherent characteristic of the absorbing species. So when the solute gets close to one another, their molar absorptivity changes. At very high concentration, the solute becomes the solvent. And moreover, non-absorbing solutes in a solution can also interact with absorbing species and thus alter their absorptivity. For UV and visible spectroscopy or spectrophotometry, okay, a liquid sample is contained in a cell, and we call that cuvette. Okay, a cuvette has a flat surface, usually that's made up of silica. Okay, um, the glass, there are two kinds of cuvette. It's either a glass and the other one is quartz. Glass is suitable for visible, okay, for visible spectrophotometry. And however, glass is not suitable for UV spectrophotometry because glass absorbs UV radiation. And most often, the path length of the cuvette is 1.0 centimeter. For infrared measurements, okay, the cells are made up of either from the sodium chloride or potassium bromide. For far IR, the polyethylene cell is rather used. Okay, in the operation of spectrophotometry, first is we record the um, baseline absorbance with reference to the solution. So what we do is we get the absorbance of the pure solvent or the reagent blank to get a baseline information. Okay, and then after we get the wavelength or of the absorbance of the reagent blank, then we subtract the baseline absorbance from the um, absorbance of the sample. Although the instrument is perfect, there would be some um, how do you call that? There would be some limit of uncertainty. So plus and minus absorbance. So here, after we obtained or after we have recorded the baseline information, the baseline absorbance, we now um, read or measure the absorbance of the sample, and then the we subtract the absorbance of the reagent blank. But in some spectro photometer, you don't need to subtract the absorbance of the blank. Okay, the instrument usually adjust. Spectrophotometers are most accurate at an intermediate level of absorbance. Say for example, the range is 0.4 to 0.9. And of course, you don't prepare a solution that is too concentrated, otherwise the light could not penetrate. And it's not also advisable that you prepare a solution that is very dilute. If too little light gets through, that's low absorbance, it's hard to distinguish the difference between the sample and the reference. Okay? It is desirable to adjust the sample concentration so that absorbance falls within the intermediate range. So if the sample is too concentrated, you may want to dilute so that the range of absorbance falls within the intermediate level. Okay? And then compartments must be tightly closed to avoid stray light, which leads to false reading. Just like what you can see in the demonstration. Okay, after you have placed your sample in the cell holder, you must tightly close the cover or the covering of the compartment. Errors in spectrophotometer may arise from the following. Okay, electrical noise. The less noise in the instrument, the lower the concentration of the analyte that can be detected. And cell positioning must also be practiced. Okay, if you are using a square cuvette, normally um, the side here is transparent. Okay, and the other side somewhere here is coated. So when you place the cuvette in the cell holder, the transparent or the clear side must the side that faces that is facing the the opening where the light comes out. Okay, so caution: keep all containers covered to prevent from dust from entering. Dust scatters the light, so make sure that the room, when you operate spectrophotometer, the room must be free from dust, because light or dust scatters light, which appears to the spectrophotometer to be absorbance. It alters, so the dust alters the absorbance. So if your solution has undissolved solid, it may be necessary to filter the final solution with very fine filter. Okay, because even the tiny particle absorbs the light, so it will lead to false reading. So preparation of solution is very critical, no, before you subject your solution must be homogeneous. Okay, colloids or suspension um, does not work. Okay, handle the cuvettes with tissue paper or soft tissue to avoid putting fingerprints on the faces. So I mentioned this in the demonstration, no? Wipe the cuvette um, on top, no, on top of the or above the cuvette, above the marking line. Okay, and keep the cuvettes clean before using. For best precision measurement, place the cuvette in the spectrophotometer as reproducibly as possible. Okay, random variation in absorbance arises from slight misplacement of the cuvette in its holder, or turning a flat cuvette by 180 degrees or rotation of a circular cuvette.